All right, moving into part 2 of chapter 13. We were talking about the rate of the reaction, and now we want to look at some examples of calculating rate of a reaction. So I have a couple of examples up here at the top of the page. So imagine we have a situation, we're looking at the concentration of a reactant, and it goes from 1.22 molar down to 1.10 molar over a 15-minute time period. What would that be in terms of the rate of the reaction? So we said before the definition of rate is the change in concentration of the reactant relative to change in time. In this case, our change in concentration, our concentration goes from 1.22 molar down to 1.10 molar, and our change in time was a 15-minute time period. Right, so doing that subtraction, that's a fairly simple one. I think I can do without my calculator. 0.12 molar is our change in concentration divided by the 15-minute time period. That would be 0.12 divided by 15, 8.0 times 10 to the minus third molarity per minute for our units. Now, units here can get a little complicated. We know molarity is actually 2 units, so sometimes this will be split into moles per liter for the molarity, in which case this would be moles per liter minutes. You can write these with superscripts as well, so this could be moles liter to the minus 1, minutes to the minus 1, using minus 1 to indicate on the bottom of that stack of units. Okay, now a little later, maybe in the same reaction, concentration goes from 0.42 molar to 0.22 molar over 2.3 hours. What's the rate here? Right, we would have same set of information. We'd approach this problem in the same fashion. Our change in rate would be 0.42 molar minus 0.22 molar, and we divide that by our time interval, 2.3 hours. So in this case, this would be 0.20 molar divided by 2.3 hours. And over this time period, 0.2 divided by 2.3, our rate would be 8.7 times 10 to the minus second. Although the units are different, it's molarity per hour. Right? And this is something we have to watch out for. Molarity per minute up here, molarity per hour up here. Right? And then the third question here is, can we compare these rates? And the answer is, well, yes, but we need to be careful. We need to make sure we're using the same set of units. This is a larger number than this. That doesn't mean that it is a faster rate. Right? If you look at the data, it's clear this is later in the reaction after the concentration has gone down. To compare, we really want to get the same set of units. So let's take that number we just calculated, molarity per hour. If we want to change that to molarity per minute, we're going to have to cancel out hours and change our time unit to minutes. So there's 1 hour for every 60 minutes. We'd need to divide by 60 there to end up with the same set of units as we had in the first calculation. So if I divide that previous answer by 60, I get 1.4 times 10 to the minus third in terms of molarity per minute. Now the exponents are the same. That makes it a little easier to compare there. 1.4 is a smaller number than 8. So the rate has indeed gone down quite a bit as the concentration of the reactant went down. Okay. Now, rate is, right, we see there that as the concentration of the reactant goes down, the rate is going down. It's actually a fair bit more complicated than that, and that's a lot of what we're going to get into in the next couple videos. But the rate of a reaction is affected by basically 3 different things. Rate is affected by the temperature in a fairly straightforward fashion. As the temperature goes up, the rate goes up. Now, this is almost universally true, right? If you're cooking at a higher temperature, you're going to cook your food faster. As the temperature goes down, the rate goes down, right? This is true as well. If you want your food to last longer, you put it in the refrigerator or even the freezer at a much lower temperature. The reactions that would cause your food to spoil are going to be a lot slower. Another way to affect the rate of a reaction is catalysis, or using a catalyst. And a catalyst does just that. Catalyst changes rate. Now, we usually only use the term catalyst to describe something that makes the rate faster, that helps the reaction happen more quickly. If something causes the reaction to be slower, it would often be referred to as a poison. Right? This is particularly true for, say, the catalytic converter in your car. The catalytic converter is helping the reactions that remove some unwanted pollutants from your exhaust stream, helping them occur fast so that the reaction can happen as the gases pass through the catalytic converter. Right? Anything that sticks in your converter that causes it not to work would be referred to as a poison. Right? Even though it's really doing the same thing, it's changing the rate of reaction, it's just changing it in a slower direction so the catalytic converter isn't doing what you expect it to do. Now, we'll talk about catalysts a little more when we kind of get into reaction mechanisms and seeing how the catalyst might change that. But the one we really want to focus on is concentration. Now, we see from the first couple examples, concentration goes down, the reaction gets slower, but there's more to it than that, and we need to talk about exactly how we can determine the way the rate is affected by concentration. And that is by what is called a rate law. So a couple examples here at the bottom of the page. I'm going to look at this same reaction, and we want to talk about how the rate law takes into account what's happening in this reaction. But let me jump to the next page real quick here, where I sort of have a generic of how we define the rate law. So I have a generic reaction here. I have lowercase a moles of reactant A reacting with lowercase b moles of reactant B to make a product X. The rate law here, this is the form for the rate law that I'm showing here. The rate of the reaction is going to be equal to K here, and this is a lowercase k. This is the rate constant. It is different for every reaction, but it's there to help the numbers match up and also to help the units match up. That's something we'll have to look at. The only components that show up in the rate law are the concentration of the reactants in the reaction. So capital A is a reactant here, capital B is a reactant here. Now, what's unique about rate laws are these exponents. So I used M and N here to show these do not necessarily relate to the stoichiometry of the reaction. They actually relate to how the reaction happens in terms of how do molecules bump into each other, what order do bonds break, form, etc. in the course of the reaction. The only way we can determine what M and N are is by experiment, by doing an experiment and seeing what happens to the rate of the reaction. Now, it's important to keep in mind, they're not the stoichiometry. Sometimes they will accidentally be the same as the stoichiometry, but you can't look at the stoichiometry of the reaction and know for sure what those exponents are. So let's come back just a little higher in the notes, previous page. If this is my reaction, the decomposition of N2O5, the rate here for the rate law is going to be equal to K. So that's the rate constant times the concentration of the reactant, just N2O5. Now, this is going to be raised to some exponent, and I'm going to call it X since we don't know what it is yet here. And what X tells us here, it relates to how the reaction happens. Right, which is sometimes called the mechanism of the reaction. It's something we'll talk about by the time we get to the end of this particular chapter. And the only way we can know this is by doing an experiment. So the value of X, I missed an N there, is determined by experiment. Okay, and that's what we'll need to talk about next, is how can we look at an experiment and get some information about what is the rate law that would govern that reaction.